Here we have Yangyong Zhang from the Success Lab at Texas A&M University. Thanks.
Thank you. Thank you for the intro. All right. So we've heard a lot of studies on the speech recognition part. And by changing like a little bit your mindset, so we're actually thinking that it is very good to know what's after the speech recognition part. So this brings me to here, talking about what is semantic misinterpretation, and then for the voice assistant apps, and then how we actually systematically study it. So smart speakers or voice assistant. These devices are becoming really popular, and like news and rumors are coming out every day. And you can see Amazon Alexa skills already topped more than 80,000. So these are like big companies that are coming out their own like devices and products. You have Siri, you have Alexa, you have Google. So people are talking to these devices from all places, from your workplace to your home to even your cars. All right. So let me ask you a question. Do you really trust or do you really know who you are talking to, these VAs? So I'm going to answer this question by sharing you some Twitters, right? I think people love like tweeting, right? So firstly, Joey. Joey shares a story about a couple in Portland. So these couple's private conversation was captured and being sent to a friend who is on their list, and this is all done by the one Echo device. And this is clearly a privacy leakage, right? And we just don't want these unintended functionalities to be happening. All right, and what's more? So we have Jennifer here. She's trying to play some YouTube videos, and it turns out to be some crazy like kids music, and this is definitely wrong. And we also have the continuous like rumors about these VA devices are spying your life. So really, this is how the people are thinking about. So we definitely want to dig deeper. So we check the definition. So what is a voice assistant? So according to the definition, this is simply a program that talks to you, and it tries to complete some tasks. And then it's based on either your voice commands or whatever it is like collecting. So this definition clearly tells you like the good story about what is the studies in this field. In the existing work, you can see from our previous like speakers and from the previous year studies. So people are trying to inject these voice commands, these malicious ones, to the acoustic channel. But the assumption is you have to be in really close range. For these high-frequency-based attackers, so you might need to just hold like a gigantic speaker like to attack like target, right? So and it's mainly targeting on the speech recognition part. Okay, and so on the other track, so people are more focusing on whether these VA devices are completing your tasks. So, so it's about the speech misinterpretations. So it changed the assumption by we're now going to attack you in a remote manner. And then, so this is also where we're very interested in, and we're thinking of this more like a computer program rather than a black box thing. So, so previous studies, since last year, people are talking about they're observing that these VA devices are returning you some unintended functionalities, even though you are talking to it correctly or you are thinking you are talking correctly. So our work, so we are trying to unbox this black box thing, right? Because it's running in the back end, and all the platforms are in the closed development, so you don't know what's in there, right? And then we also want to propose a kind of systematic way to study this problem after the speech recognition, which is from the speech, the audio, to text. All right. Let's recap some of our research questions first. So firstly, you want to say what's in the black box of these VAs. So in that way, we're going to define the problem of what is semantic misinterpretation. Then we want to see what's the root cause of this semantic misinterpretation. Lastly, we are trying to propose a way that we can do like to probe this problem in a large scale. All right. So first, what's inside the box? So based on our study, we did a lot of programming stuff, and we read a lot of materials from these platforms. So a lot of rumors and different things. So we come with this like architecture. So firstly, you're having the the ASR part. You're translating your audio to text. So then you're using they're using the text information through the NRU part. You're going to extract these user intents. It's very similar to the Android intent message, right? And then by using these intents, users will be directed to these vApps. By doing so, these vApps is going to give you the response, and it's going to be rendered and played to you. This is actually how everything works. Okay, in our work, we are actually very interested in studying only one part of the problem, and this is the intent classifier of the NRU part. And let's see what's the definition of semantic misinterpretation rather than the speech misinterpretation. All right, here we're like just saying, even though your ASR is working perfectly fine, the NRU still may exist some errors and may result in some like unwanted functionalities. Let's see the example from Jennifer. So she wants to play the YouTube videos, but it turns out to be some crazy kid stuff, right? So this is definitely wrong, and the consequences can be much serious. People are now doing the purchasing, doing the navigation, doing the gaming stuff, and you're doing all sorts of things. And what if some malicious people are registering something in the App Store, and this can definitely be wrong. And currently, the most feasible way of attacking these is using so-called squatting attack, and I will be telling you some details. But before that, we want to see what's the root cause of this whole problem set. So we have third-party developers. They're trying to program the app, right? And then how they do it is they're trying to think of what's the possible ways like a people or any human being can talk to your device, can talk to your app. So for example, here, Alexa, install the true bank scale. This is something that he or she can think of. And then inside the intent classifier, there's a tree kind of architecture. And then if your user says this voice command, the intent will be coming out as a result. Similarly, if you have other voice commands, you simply integrate your voice commands to this unified classification tree that is used by thousands of apps. OK, so what is the squatting attack for the vApp? So for example, if you have the the true bank scale, so if a malicious people are registering some malicious app that is named the truth bank scale, and if your users are accidentally speaking the truth, and so I can tell you it's very likely because we see a lot of results. So he will be directed to the malicious one, right? So we have talked about the problem. So we want to probe this problem. We want to study this problem in a systematic way. So we come up with this tool called LibFuzzer. So it is trying to fuzz what are the potentially very dangerous voice commands. So how people can speak one single voice command in different ways and can direct you to a malicious app. So we have this strawman model. It takes the seed voice commands and it tries to mutate your voice commands. But the problem is there are simply too many options. You can mutate from A to B, B to C. You have Apple and Beeple, right? There are just too many stuff, and they're just useless. So we come up with this idea of we want to learn from the linguistic knowledge. OK, so that we are going to reduce the search space and then find out these potentially mutated voice commands that people are likely to say. And so for the convenience, we are trying to define a concept called lepsis. So it is something beyond the normal speech errors. So it's more like any form of mutated voice commands that can make the machines that misunderstand you. So for example, there's a San Francisco accent, right? So definitely so you just cannot say they're like speech errors, but they're just like a specific group of people, they're speaking differently. So these concepts is not like actually well recognized by the current systems. And when you develop, you can definitely make it wrong. And also, we are creating new vocabularies, right? And then we have the regional language, we have different kinds of things coming up every day. So definitely, like the lepsis is like a general concept of how these voice commands can be speaking differently and can be dangerous. Okay, so here comes the solution. So we try to model these linguistic knowledge using the Bayesian networks, right? So that we're going to shrink the large search space, only resulting in some likely spoken mutated voice commands. All right, it's the lepsis. So that by doing so, we're able to pinpoint the problematic voice commands and help to start eliminating the problem. Okay, having talked about the whole tools, so let's see some evaluations about the lepsis and also the Lei fuzzer. So we designed this experiment to see, because since the problem can either from the ASR or can also from the NRU part, so we want to see whether it's the ASR or the NRU that are like playing the major role in this problem. So how are we doing that? We collected 109 real lepsis from the MTurk user. And so we want to use these lepsis, and then we play these audios to the VA devices. And then we see that only 23% of them are from the ASR. And 77% of them are from the intent classifier. So mainly, this is talking about that even though the ASR is working perfectly fine, the NRU part is still having some problems. Okay, then we also use our tool to scan the stores. So we crawled more than 30,000 of apps from Amazon Alexa, and also more than 2,000 from Google. And then we generate more than 500,000 lepsis. And then we try to verify these lepsis using examples. Of course, it's like taking forever. And then we just play these synthesis audios to the Echo or Google Home. And then we try to verify if it's coming up with the right, functionalities. So as a result, we found like more than 70% of the Amazon Alexa are like giving you the wrong thing, and then almost 30% of Google. So it's very interesting, I think. And also, this is just the theoretical stuff. So we want to attack in the real world. So we upload an app named the True Bank Scale, and we also upload several malicious ones, and then we ask the users to play with this True Bank Scale, and we find out there are 4 of them are being triggered, the malicious ones. So this is definitely something real. As a summary, okay, our work tried to unbox the black box of VA platforms, and then we try to pinpoint the intent classifier problems that is very, very related to the third-party VA app developers. And we try to find these potentially dangerous voice commands, like in a large scale. And we show there's a very early signals that there's simply lack of security considerations for these V apps in the backend or whatever things. So for the limitations, we just think we just need more data, because collecting these linguistic knowledge is so time-consuming. We need more data, we need more knowledge, and then we want to use better modeling and also better machine learning techniques. I'm sure you guys are better than me. So that's the limitation. Okay, takeaways. So we can see from the app population, these V-app populations are growing very fast, similar to the mobile apps. So you can see some statistics from the year 1 to year 5. So I think definitely this is very important field that you can study for. And also, what's after the NRU part? What are these apps are processing in the backend? So I can tell it's pretty wild there. So yeah, I think it's very interesting to see what's after. And also, we are trying to dealing with more human factors in here because your input and output is in a vague natural language. So this is definitely, we need to jump out of the box and to think of the solutions and the tags. Okay, I think that's it. And we have our tool being published. So just jumping and test it out. Thank you.
All right, if we have any questions, feel free to step up to a microphone and ask. I've got plenty while we wait to see if any audience members are so bold. I'm curious about, so when we look at these voice services like Alexa, there's an ASR unit that feeds into this natural language understanding unit, NLU. What wasn't clear to me in the talk was how are you actually sure that you're isolating the NLU? Like you had this slide where you say 23% of things are ASR errors. How do you know what's the cause?
So in Alexa app, you can actually see the history of what you're saying. So by checking the text output, you can make sure whether it's wrong or not. So simply by doing that. So basically, what they play to you is the ASR result, the text output.
Okay, thanks. Yeah. Question?
Sure, Joe from UC Irvine. So I want to ask about the defense. So I wonder, because yesterday, and I hear talks about defending machine learning algorithms, say using invariants, and I know previous works using certification, and to defend against those kind of adversary samples. So is it possible to apply those kind of ideas to make your, say, either ASR or the later stage more robust against your attacks?
Okay, so for the defense, I'm thinking for my study for here, so these how to say, the intent classifier relies heavily on the human efforts because you need to manually come out everything. So for defense, what we can do as the best effort is to generate these how to say, the lapses when developers are developing these voice commands, so that we can telling them that what are the possible things that people can make wrong. I think that would be the best defense for now. But definitely there can be other techniques being used. Yeah.
Okay, thank you.
All right, so returning to my previous question, I'm going to commit a session chair faux pas and get a tiny bit adversarial with my question. To be clear, I think the work is really interesting and important. So in Alexa, the output of the automatic speech recognition system is actually a distribution of possible interpretations. Yeah. And then I think it's also actually a probability distribution after it passes through the NLU unit as well. Yeah. So when you're looking at that output that you actually receive at, say, your skill, is that, can you be sure that that wasn't tainted by the NLU component? Or are you getting, is there a bypass where you purely get just the ASR component there?
Oh, I think, so our previous architecture shows, right? So it's based on a text output that these backend intent classifiers are generating these user intents. So I think from what we read, we're pretty sure. So what this history is showing you is the isolated result of the text output of the ASR. I think this is it.
Nice. All right. One more question. So you mentioned the limitations of the data set is a problem. I also know that this is a big problem. I'm curious, do you have any strategies, or you're just going to go bigger and badder with the MTurk? What's your thought for that in the future?
So currently we heavily rely on ourselves. We are finding these linguistic knowledges and we input the rules. And as you can see in the tool. But I think in the future we can automate the parser step, because say you have a correct version of your voice commands and you have the outer ones. then you just compare them and generate these rules. I think it's going to be pretty good.
All right, great.
Thank you.
So yeah, we're going to get out to the coffee break a bit early. Let's thank all of our speakers one more time.